Yeah, maybe.
Not to find it.
But
It's small.
yeah, and it's smaller.
Get your research process.
I don't know. I also.
Yeah.
I tagged out on the
Oh, okay. Yeah.
Hey, man.
Like, you don't have to say that question. I said your turn.
Eager, but it turns out I showed up right on time to get the best seat in the house.
Yeah. Well, no one wanted to hear about elevator pitches much today.
He really wants me to do the clinical translation research for Egypt. This was in psychology.
Oh, yeah.
I don't hate the idea of getting my PhD, but
This is research topics, and the rules of engagement are Dorothy will be speaking for 20 minutes. And at the end of that, we will open it up for questions for her and anything else. So feel free to ask any question about anything, with the exception of maybe world peace and some other issues dealing with Washington, which I think I want to discuss. And I'd like to thank Dorothy for agreeing to do this. And remember what it is, it's just to sort of get a flavor of it, so you'll encourage you to take a deeper dive. And if anybody wants to do one of these or the career matters, please let me know. It's not that painful, is it? No, we'll find it.
You don't know it?
Not yet.
And with either research or career, pretty much anything is wide open. So if you're passionate about something, let me know, and we'll negotiate. You get to choose what kind of cookies or whatever. Thank you. Go ahead.
Yeah, thanks for having me. So my talk today is called The Significance Delusion, Inconvenient Truths About P-Values. And I apologize in advance if I insult anyone's intelligence here in the room, but I really wanted to take it back to the basics, just to make sure everybody knows like the real truth about what P-values really are, what you can do with them, what you can't say with them. So again, the premise for this was, it's been written in the last decade or so about the misuse and misinterpretation of p-values, and journals have been publishing incorrect statements from researchers, and kind of the statistical community stepped in and decided they had to take some action because there was a lot of stuff, publications out there with just wrong conclusions and things like that. But it's kind of a tough nut to crack because it's just kind of entrenched now in the process, and so hopefully it's by getting more awareness out there, and I think it's moving in the right direction, but we just have to kind of keep on it. So I'll just start with a brief overview. I'm going to talk about what the definition of p-value actually is. I'm going to give some examples of things that people have said as their conclusions from p-value findings, and we can figure out if they're true or false. Talk about the significance game that's kind of played amongst researchers in getting things published. Talk a little bit about the value of p versus significance testing and why they're not exactly the same thing. And a big question that people always want to ask when they do some research or an experiment is like, how sure am I that this is a real finding? And then talk a little bit more, circle back around to the kind of reproducibility crisis in scientific research. So what is a p-value? Well, there's a pretty strict definition of what it is. It's a probability. It's the probability of when you perform an experiment, one single experiment or study, what is the probability of you getting seeing data that you have seen or anything more extreme, basically, given that the null hypothesis is true. So assuming that there, for example, if you're testing two groups, you assume that there's nothing going on, what is the probability that you would see the data that you have observed or anything more extreme than that? That's basically what it is. That's not always what people interpret it to be, unfortunately. So a few examples that we've seen in the literature. I get a p-value, it's more than 0.05, and I conclude there's no effect in my study. Is that a valid conclusion to make? Well, it is true that the larger your p-value, and I'm not going to define here what I mean by large, because a p-value is actually a continuous measure. The larger the p-value, the more the null effect is consistent with the data that you have seen in your experiment. But the null effect, the fact that there's no effect, isn't actually the most likely effect, given what you observed in your study. The most likely effect is actually the one that you've seen from your experiment, regardless of what the p-value is. So the effect is different from the p-value. That's a concept that you should hold on to. If I get a p-value that's below 0.05, I want to say the finding is scientifically important. Hey, I'm onto something here. Well, some of you probably already know, like p-value, just because it's statistically significant doesn't necessarily mean it's an important finding, whether it's some clinical finding or laboratory finding, whatever it is. So scientific significance is a completely different beast from statistical significance. So keep that in mind too. Okay, we got two different studies. I got this one over here that found they were doing the same work as this one over here. This one found like a small p-value. This one found a large p-value. Are they telling me different things? Do I have conflicting evidence? Well, again, the effect and the p-value are completely separate things. So in this example here, we have in scenario A, you have two studies where they found the same effect, but their p-values are completely different. The one on the left in A has a large p-value, not much confidence in the estimate of the effect, and the one on the right has a small p-value, but their effect that they measured in the studies are the same. In scenario B, we have two studies that have exactly the same p-value, but they have varying effects. So in those scenarios, in scenario A, with very different p-values, those studies are actually very inconsistent. So something here's I put these two together because they're basically the same thing. And I have p-value 0.2. There's 2% probability that my null hypothesis is true. Can I say that? I have a p-value 0.03. There's a 3% probability that my result is due to chance. Is that a valid conclusion to make? Well, actually, neither of these. You can't even go there, because if you think back to the definition of the p-value is actually calculated under the assumption of the null hypothesis. So I can't possibly tell you anything about whether the null hypothesis is true or false, because you're assuming it to be true in order to calculate the p-value. Same with that. Same again. Same scenario. So p-value 0.01 under the null hypothesis. So now we're assuming null hypothesis. These data would occur 1% of the time. It seems kind of reasonable. But actually, you always have to remember it's not exactly the probability of seeing what you saw. It's the probability of seeing what you saw or anything more extreme than you saw. Is how the p-value is calculated. So if you said true on this, I'm going to give you half points, but it's still not straight true. And finally, so you got p equals 0.05. If you reject the null hypothesis, the probability of a type 1 error is 5%. So I'm going to come back to this in a little bit, but p and alpha, the type 1 error, have absolutely nothing to do with each other. They're totally incompatible. So don't confuse the two. But there's a reason why people get muddled up between those, and I'll come to that. So basically all of those are false. With 7 being the closest one, number 7 being the closest one to a valid conclusion. So I think for me, the one, and there's 100 of these out there in the literature, but for me, I think the biggest one for me is the one where people believe that the p-value is the probability of them making an error, because that's not what it is at all. And the probability of your finding being false can't even be calculated from a single experiment without other information. So what's going on? So in theory, we saw p-value is it's actually a random variable. It's a data-dependent measure that's continuous. Nothing magical about 0.05 to measure evidence from a single experiment or a single trial. And in practice, what we do with p-values is we calculate them and we chop them up into like little baskets and say, this is strong evidence, this is weak evidence, and we use these like magical cutoffs that there's not really any reason for using. And we play the significance game. So this is actually from a blog, it's way back in 2013 with Michael Hankins. He actually gathered like something like 500 and something expressions for basically borderline significance, which were put in their publications, but they're just desperate to get the thing published. So they say marginally ahead of significance, approaching, trending to, and it's like that they have to get close to this 0.05 and that there's something magical about it. And it's a game, you know. He also did a Google Scholar search of the term margin of significance, and he got almost 19,000 articles that, and plotted the p-values and did a density graph of, you know, with the magical 0.05 and 0.1 10% cutoff. And as he said here, it's like, yay, we made it under 0.05, or between 0.05 and 0.1, we're in the region of declining hope, and above 0.1, it's like, forget it, we're out of here. And that's kind of like sometimes how these, you know, when we're trying to submit something for publication, that's kind of the feeling we get, and sometimes that's how it's perceived. But we shouldn't be playing that game, and we don't need to be playing that game. So what can we do? Well, we can blame the statisticians. Like, we go back to like Sir Ronald Fisher back in the early 20s wrote the book Statistical Methods for Research Workers, which was highly regarded, and he did a lot of work on agricultural studies, controlled trials in agriculture, and he was trying to set the rule books for this. And he came up with a p-value, and he chose a 0.05 as what his preference was, and said, but basically he just said, this is suggestive that this experiment, it's like worth another look. There's maybe something going on. It's not, I found the answer to everything. It's just like maybe worth another look. And then we have these guys. This is Neyman and Pearson, who some of you might know from some statistics books. And these guys were actually rivals of Fisher. They hated each other. They did not agree on anything, and with they never became friends till the day they died. They completely kept their separate ways and did not well, they argued with each other a lot, and their kind of philosophy on this is completely different. So we have Fisher, who kind of invented the p-value. He explained what it was. It's a continuous measure of evidence for a null hypothesis in a single experiment. It's calculated from the data. It's observed. It's a subjective decision on what to do with it. And then along come Neyman and Pearson, and they developed this theory of hypothesis testing with alpha and beta, with error levels and power that are determined ahead of time. Nothing to do with a specific experiment. The alpha and beta error levels apply to multiple repetitions of experiments. So in the long run, what's going to happen? And they turned it into kind of objective behavior based on a rule. And what happened was, and if you see here I've written P and alpha are completely incompatible because alpha is like long-term behavior and P is calculated from your data on a specific experiment. But what happened was these guys couldn't agree, and over time their two philosophies have kind of morphed into this one thing, which is what we do today, significance hypothesis testing. So it's kind of unfortunate that they had separate philosophies and now we have this kind of hybrid mix of what was going on. So I call this statistical alchemy. So we have uncertainty and everything's uncertain out there. We don't really know what's going on. We can try and quantify it, but we have this yearning to get to the truth. And I call p-values the ultimate statistical alchemy because everybody wants a magic wand. But what it really is, I call it uncertainty. So we're trying to pretend that nothing's uncertain anymore. We just want an answer and we want a decision. So that's kind of how people do things. So this is just a quick example. Back in 2010, there was a professor and his student. They were doing political surveys and they wanted to find out if more left or right-wing people, did they see the world more in black and white? And so they did the survey and they had 2,000 participants and they discovered that moderates perceive shades of gray more accurately than those on the left or right. So they see things black and white and people in the middle can do all these shades of gray. So they thought they had this great, it's like, look, I got a low p-value, and they thought, great, we've found something, this is great. And then the professor said, actually, because it was just easy to do, he said, well, let's try and replicate the study. So let's try and replicate the study. And he thought it out really well. He got 1,300 participants. He calculated from 99% power to try and get the same effect as he'd seen the first time. And so they thought this is going to be great. And they did the study, and they got a P of 0.9. So what does that tell us? Never try and replicate your data? No, I don't think that's what he tells us. Like, replicating your study is a bad idea. No, I think it was a good idea in this case because they kind of dampened their enthusiasm for their first finding, which was probably the right thing to do. So if you're surprised by this, you shouldn't be, because actually they figured out that the probability of getting, you think you got power at 99%. So people think, well, we got a really high chance of being able to get the same effect, but it was actually closer to 73%. And if they wanted a really significant result, so a small p-value again, it was actually only 50-50. So it was just as good as tossing a coin. So the big statement, most research findings are false. There is actually a paper, that's a good paper that's been written with that title. It's in my bibliography. But the probability that your finding is true or not, you can't tell from your experiment, like I said. It's not the p-value. It depends on a lot of things. And turns out one of the biggest things it depends on is what is the actual probability that your hypothesis is true before you even start the experiment. What are the odds of what you're going to look for actually being a true thing? The truth. So this is a paper from 2014. Where they looked at different levels of, prior chance of there being a real effect. They measured the p-value, and then they modified the p-value using some Bayesian techniques based on what is the prior chance of the hypothesis being true. And as you can see, if you look at in the bottom line, the difference between, within the first two, within the middle two, and within the two on the right, there's less difference than between the blocks going across. And that's because it depends on the chance of the hypothesis, the real effect, before you even start your experiment. So if there's a low chance of the effect actually being real, then your p-value really is not going to tell you very much about your finding at all. So I think this is like a good wake-up call for folks to say, like, it doesn't matter what the p-value is. Everything kind of, well, it doesn't matter what the p-value is, but that's not solely where your focus should be. There are many other things going on you have to take account of to figure out if what you're really seeing is what you think you're seeing. So why don't we just report false positive risk or the false discovery rate instead of the p-value? Well, the problem is we don't really know what the prior probability of our hypothesis is before we do the experiment. Maybe if there's been a lot of experiments done before, then you might have some kind of idea where to go with that. But if you don't have any idea, there are other things you can do. You know, you can specify the probability needed in order to achieve a false discovery rate or a false positive risk of, say, 5% or 10%, as well as the reported p-value and its confidence interval for any effects. Or you could just assume a prior probability of 0.5, like it's a toss-up, I don't know. Or, and then calculate what would be the absolute minimum false positive risk that you could get given the p-value that you saw in your experiment. So it just gives a lot more information, and I think it kind of downplays the focus on the p-value. This is a paper that just came out in December 2017, where David Cahoon actually did this, and he did a lot of simulations to show that, you know, the bigger the false positive risk is always larger than the p-value, but how much larger it is depends on the plausibility of your hypothesis. And so he showed that in this graph here, if the probability of your hypothesis is, say, 10%, and you get a p-value of 0.05, it actually has a false positive risk of 76%, which is quite surprising. If there was a 50-50 chance that the effect is real, then that comes down to 26%. He also calculated that in order to bring that false positive risk down to 5%, which is what some people think the p-value is, the p-value actually has to be as small as 0.0005. So there's kind of a lesson there that's like, well, if you really want to know if you found something that might be meaningful, your p-value has to be pretty darn small. So just quickly, I don't want you to read all this, but I call this the natural selection of bad science because this over-reliance on p-values and significance testing really has evolved into standard practice. And there's a reason for that, because I think researchers are rewarded for publishing and publishing as much as they can, as fast as they can, and they're incentivized for that. And so there's some tools out there that, you know, anyone can now run statistical software, and they get p-values spat out, and they report them, and they get them published. And journals are more likely to publish positive results than negative results. But I think it's, you know, negative results are still results, and I think the field is shifting a little bit. It's improving, but it's definitely been a problem in the past. So just quickly, the reproducibility crisis in science. So there's been so much written on p-values and what interpretations, and just one after the other over the last decade. It's just never ending. And then finally, in 2016, the American Statistical Association came out with a statement on p-values about their purpose and their interpretation, and just tried to rein the whole field in and say, look, this is what you can do with p-values, and this is what you can't do with p-values. And so it's a longer paper than just the 6 principles that they came up with, but they came up with like 6 main points that they wanted everybody to get about what p-values can do and what they can't do, so they can indicate how incompatible your data are with a specific hypothesis or model. They don't measure the probability that your hypothesis is true or that your data were just by chance. You should not be basing policy decisions or interventions based solely on whether a p-value is below 0.05 or 0.01 or whatever you happen to choose. Proper inference requires full reporting and transparency. There's a whole other talk I could give on reproducible research and transparency of reporting and things that should be reported alongside, you know, p-values and confidence intervals. A p-value does not measure the size of the effect, and the size of the effect is actually more important than the p-value. And by itself, you can't do anything with a p-value by itself. It's not the be-all and end-all, and we don't need to ban p-values, but I think they just need to be interpreted, used properly, and augmented with a whole lot more information when we're trying to publish results. And then just a few more points. Yeah, they're limited tools. We need to use them and interpret them appropriately, and they shouldn't be solely used for conclusions. We need more emphasis on complete reporting and estimation. And just the last two things, the p-value is not the false discovery probability, and the evidence you have in your p-value as a standalone number is actually much weaker than the number actually suggests. So I'll just keep that in the back of your mind. Okay, and I have extensive bibliography if anybody's interested, and more than that, I'm happy to share that with you. So thank you.
So these talks always make me nervous because I realize that everything I've done for 40 years is wrong. That's always a hard thing to do. So is it? So I'm right. I do an experiment and I get because I often measure multiple different things. I'll have something that's p-value when I run it, it's less than 0.05, and then I've got one that's say 0.7, and I go, great, this is great. I got 0.5, that's good. 0.7 can actually be good too because it says I need to do a multi-center trial and keep me in business for 5 more years. But so do I still refer to the one element that I measured with less than 0.5 is statistically significant? Is that how I write that? And then the 0.7, since you told me what I can't do, which is, it's a whiff of significance. How do I refer to that?
Yeah, I think people need to get away from the statistically significant and not significant, because that's the 0.05 hard cutoff, and there's actually no reason for that. And like I say, just evolved from Ronald Fisher back in the 20s saying he thought that was maybe a good idea, but it's like 0.05. I would say it's like when somebody from the lab comes to me and shows me 2 assay results, and I go, oh, that one's bigger than that one. And he goes, actually, they're comparable because it's not more than a log difference. 0.05 is not different from 0.07 in my book. There's no magical distinction between these two numbers. They're on a continuum, and they're not that much different from each other. So
there's the statistical reality that you've now illuminated. And then there's reality, which is the reviewer at the other end of the internet who is now beating me up about how I refer to the 0.7 result.
Right.
How do I? So it's really how do we?
So I think we need to re-educate the reviewers.
Yeah, right.
I know that sounds like an impossible task, but come on, everybody all together now. I mean, like I say, it's a tough nut to crack because it's entrenched, and people read papers like that and then they go off and do the same thing, and so it's kind of self-perpetuating. But I think if we can just keep nudging it a little bit in the right direction, then I think we can eventually get there.
But one trend I see, which I think is good, is where people say, well, I got this result which was statistically significant, but the difference is not clinically important.
Right. Right.
And then that leads to a really interesting discussion about what is clinically.
Right. It's just not always depending on the.
Yeah, that can be very illuminating when you ask the question, I'm measuring X, what's the clinically important difference for that? And somebody says, no one has a clue.
Right.
Well, maybe part of it also is when you're writing your methods, don't spend like that much of a page on your exact nitpicky cell culture conditions or your these kind of criteria, and we're all guilty of that. I mean, maybe at least in the immunology field, and then the statistics part is like one sentence. It was done in Prism. So if you probably buffer the statistical part, I would. By actually talking to a
whatever SPSS said.
Whatever SPSS said, that may be one way to sort of, counteract, preemptively show the reviewer that, look, I've given a lot of thought to the statistics. Here's all my assumptions.
Right.
Put that in the methods, and then might be less likely to get hit for a 0.07.
And Dorothy, what were they supposed to do with that ASA revision? If all the statisticians now want to move it, is everyone supposed to go talk to their favorite journal editor, or like what's the field doing with that change?
Well, I mean, I think the ASA principles that they came out with was, I think this was trying to convince people not to make such sweeping conclusions from their research results primarily, and put more of an emphasis on, that p-values are not the be-all and end-all. We need to focus more on estimation and confidence intervals. And whether you're a frequentist or a Bayesian, it doesn't really matter, but there's, they wanted to just de-emphasize the importance of p-values, because what you can actually say with them is not very much. And so they just wanted to.
It seems like some of the really big journals now all have a statistician on the reviewer panel.
Right.
So maybe they're the ones that love the hammer.
Right.
There's a couple questions. The fellow in the back.
Am I in the back?
Yeah, you.
So, I don't want to get on the reviewer thing. We all love to be reviewers, but I'm sure a lot of us are reviewers. But, it's important for us to also be the example for the other reviewers who are reviewing with us. They get to see your reviews too. You can stick up for people when they don't show statistics. You can say, we applaud the authors for not doing statistics that were not warranted.
Right.
It's because other reviewers will say, why didn't you do statistics on your experiment where you had an N of 3 for each condition? And what we try to say is, I can do that for you, and it comes out significant, but it completely violates every condition that the test requires.
That's it. And of course, the other thing is that definition of a p-value is only the probability of observing your data or anything more extreme under the null, assuming that all the other conditions and assumptions of the analysis that you did are valid.
Right.
So the reasons of why you don't get a certain size of p-value could be something to do with your data. It could be something to do with the analysis you did with the wrong assumptions. It could be any number of reasons why you get a p-value that comes out as 0.2 instead of 0.003, because there's so many things go into it. And I think a lot of the time the assumptions part of calculating p-values and significance tests is not even addressed, not even a sentence sometimes in some of the journal articles that people say I did this and this. And you're lucky if you can see a sentence saying we tested the assumptions. And journals are getting better. I don't know how much, people are requesting more, appendices and background information. They're asking, some of the top journals are asking for code and data sets and stuff to be provided, depending on how important or impactful they think the research is, so that they can check and see, did you do the right thing? Did you check were the assumptions satisfied? Is it valid? Because all of that goes into a p-value as well.
And also, I think most of us here probably do experiments where the N is 5 or 3. It's low repeats because each biological replicate takes a ton of work to do. It's not like you're not, counting birds. We're not doing that kind of work. So ultimately, some of the recommendations that I've read are, if your N is lower than 10, do not do a statistical test. It's as simple as that. If parametric or not, you shouldn't be doing one, because the test will assume that you've sampled the experiment enough to warrant the test. And the problem is, reviewers ask for the test, and you say, okay, I'll do it. It'll be non-parametric because I can't possibly assume normal distribution with what I'm seeing here. And then you do it, and to get a p-value lower than 0.1 on a non-parametric test is impossible.
Right.
so then they say, oh, see, you talked about this result in your results section as if it was significant, but your p-value is non-significant, and then you're just stuck in a ditch.
Right. And the reason there, the non-parametric tests are less powerful than the parametric ones, but there's also like the assumption that some people think there are no assumptions for non-parametric tests, and that's not always the case. Sometimes, sometimes they don't have the same, distributional assumptions, but they do come with some assumptions sometimes. So, it's not a free for all. Like I get a free pass because I use a non-parametric test. You have to be aware of that too.
So why not drop p-values altogether? Because it's trying to assess the role of random error in your experiment or your observational study. You can do that with confidence intervals.
Right.
And pay more attention to the systematic biases
Absolutely.
that are just as, if not more important.
Absolutely, and I think a few years ago, there was a journal or couple of journals actually tried to ban p-values altogether, and they said, we're not going to accept any submissions that have p-values in them. It didn't actually go very well, and they had to ban them. So like I say, this is so entrenched that I think it's going to be hard to get away from it completely, but I agree that we could probably do without them and just, do more of the estimation of confidence intervals, the effect sizes, and really completely de-emphasize them.
Any other statistical consultations that anybody wants to? Yes, so the non-parametric discussion is an interesting one because how many here actually had training in non-parametric statistics? Yeah, that's what I thought.
Define training.
Yeah.
Define training.
How many of you know about quasi-experimental design? Does that ring a bell? A couple, maybe, sort of.
What do you mean? You mean Mendelian randomization and things of that?
Power calculations.
There's a whole field of quasi-experimental design that oftentimes we should probably be utilizing in our approaches to things that don't require a full-blown randomized controlled trial or totally full-blown randomized controlled experiment with animals or whatnot, just particularly when you're searching for the truth. And I think it underscores the deficiency in our training. I mean, it's a historical one, so, I'm an old guy, I gotta tell stories. But when I was in Denver, I was working with a world-class immunology group. And one of the senior members of that group, who was just really well-known internationally for her work in listeria, called me up. This must have been about 30 years ago. And, I'm just an assistant professor or barely associate professor, I don't remember exactly when. And she calls me and she says, can I talk to you some? I got a question. So I go up and see her. She's a really nice lady. She says, can you explain to me what a t-test is? And I went, because she was a very senior researcher, and I thought, well, don't you know what a t-test is? Well, in immunology, they didn't use statistics until about 30 years ago. Is what she basically told me. And so, I sat down and explained to her what a t-test is, which is kind of a dangerous thing because so I mean, in the same vein, I think the misinterpretation of t-tests or use of student t-tests, and then the one I really like are correlation coefficients. Pearson, right? Your pal Pearson. And the misuse of those is pretty stunning. So.
Yeah, I think everybody should have that. I don't know if you've seen that multifaceted graph with all the different combinations of scatter plots that can give you a correlation coefficient of one, and I think everybody should have that.
So it sounds like based on the turnout, we should plan on a few more statistical related topics. So I'm thinking, the misuse of correlation coefficients, t-tests, and maybe a couple other things. So for what are our next two that we've got planned? Dr. Budd is coming to tell us how to interpret your summary statement. That ought to be entertaining.
And Dr. Mark Plant is doing the PowerPoint for the Career Matters.
Okay. The misuse of PowerPoint, which there are epic books written about that. And then next spring, we have a couple of things planned. We're going to do the Marshmallow Challenge for the Career Matters, which is one of my favorites. If you ask me what it is, I'll say you'll have to come. Does anybody else have, since I see an opening, what other topics would you like to hear about? What if I offered a free, like a $5 Starbucks card for good ideas that get accepted? Would that resonate with this crowd?
Not in my pocket.
I'll figure it out. I mean, I'm just looking for incentives, right? Because this is kind of a lot of fun. And we'll circulate these slides, and out of your extensive bibliography, is there, one kind of simple, let's get back to your bibliography of all those great, a couple of them look pretty entertaining. Is there one that's sort of short and sweet that would give us the Cliff Note version of what we heard today? I was thinking of the 5 ways to fix statistics look pretty.
Yeah, that's a more recent one that's going to be by Jeff Leake, who's a biostatistician at JHU, and some of his colleagues basically gave their take on, an overview
And that's
what
probably,
direction we can go in.
and that's 2 pages long, and that means it's digestible for those of us who are not. Yeah.
Which reference had the graph of the valley between the peaks, the valley of declining?
Oh, yeah, that was.
Oh, that was actually, that was on the blog. That's, I think it's on the slide, so, yeah.
Yeah, so the slides will be available online. We have a site for that. Yeah, really.
I don't know if you've done this, but can you tell about preprints and the strategy for, when to put up your preprint and maybe like journal selection, like where do you send your paper? Is it better to start high and then climb down the ladder?
Oh, that's a good one. I like that one. Yeah. That's what I like. We're training entrepreneurial spirit. Yes, that's good.
I could talk about this in the context of bioinformatics.
Oh, yeah.
Maybe or something. Yeah.
Statistics, big data.
Or bioinformatics services. I don't know. You and I can talk.
I generated a huge data set. Now what?
It's just bioinformatics.
Yeah.
What I do.
Yeah, exactly. Yeah.
Well, let's not get too close to scientific misconduct. All right, guys, thanks for coming.
Thank you.
Not quite. I'm very close. I'm doing one on Tuesday, and I pretty much know what to do.
Okay.
Did Stem Cell have any ideas for you?
Yeah.
on what-
Anytime you remember to do your
I'd love to. Basically, I wasn't putting enough separation media.
Oh, okay. Okay.
And so, I have 2 so for submitting a paper where I've got use rates for and when I look at a bar graph, it's like, okay, right? So I thought my confidence in it, well, whatever it is, there's motivation, I'm 5% sure. I was like, okay, you're not significant. You're significant, right? So my point is, I can usually tell when I'm looking at paid and small numbers.
Okay. Oh, yeah.
This is the first. This is the first one of this lecture series that I've come to.
Towards making things,
One on transfer.
and so, your piece on.
Last week I gave one.
Here.
Three people did it.
So you must cluster
They're
here.
either about
Pretty
research.
much cluster here. How much overlap? It's not very likely.
Yeah.
But people
No, that
do
sounds really cool. When are they?
value tests for the secondary,
They're generally-
over whatever.
Generally on Thursdays.
That's just so
So it's like every other Thursday.
feeling coming.
Yeah, it's twice a month.
Month.
Sends out announcements for.
I'm a master's student under.
You do it to get your article in, we're not rolling over a rock when, we're trying to over. Right? Anyways, my feeling was that, I just want to say I appreciate the location. And see mostly what is significant. I always think that is that globally fair?
Part of the big consortium, I mean, he has as many
Doing, basic science. When you're dealing with, real world, population studies or, effects in people. There's so many other parameters that you're comparing, and that's what you're trying to account for, right? It's that you're not thinking about it, and you want to account for the fact you're not thinking about it. In basic science, you pretty much are controlling checks on everything else other than what you're varying. And so these because that has not, confidence, confidence in that. Yeah, exactly. And knowing something about the technique, right? Some techniques give you very noisy data. Change those techniques have very precise noise.
Maybe I'll get
Okay.
Yeah.
I know, I have to sign off.
Right, okay. All right, okay.
I recorded, and I heard sound the whole time, so.
It's all very.
It makes sense, it's okay. But anyway, just, I wanted to introduce you because.
Yes, thank you, thank you.
Away with
Nice to meet you.
Yeah.